Alright guys, so we're going to talk about the latest WebWork for Math102, which is WebWork10, and that's on differential equations. So before we begin this, I want to talk about the actual reason why you're going to be studying differential equations. Because in the study of sciences, most of the time some of the phenomena are much more easier to be described in terms of the rate rather than the quantities themselves. So we're just going to focus ourselves on those phenomena which are better described by the rate, and hence the differential equations will always be described with respect to time for a certain given quantity. Okay, so we're going to start to talk about those. So there are two ways to deal with these. A differential equations solution is actually a function that obeys that differential equation. In other words, let's say if you want to find a solution of a differential equation, what you're seeking is a function whose derivative is going to match up with the differential equation. Sometimes it's very hard to find. And then what we try to do is we try to avoid finding the solution for our analysis and then just trying to focus on how does the differential equation describe the behavior of the whole situation. Okay, so we're going to start to talk about those phases in this one, and the next WebWork is going to be based on solving differential equations and then approximating solutions from there. Right now we're just talking about the behavior. Okay, let's talk about question 1. So what they've told you have a cubical crystal side X and a volume V. Right away when you know there's a cubical crystal, you can figure out the relationship between the volume and the side as V equals to X cubed. Now in this question for us, the dV/dt is given to us as a formula out here, and this expression is right here. And when you see that expression, the k and I in that expression are constants. So given that information, what they want us to do is to find dx dt. So what we can do is we can start from this relationship, take a derivative of this relationship with respect to t, and then once we have this dV/dt, we can plug that whole value in there. Once we do so, you get this whole giant equation. And then you have to isolate for dx over dt from there. In this case, you'll have a dx dt that looks like this. So now traditionally differential equations are required to have only the variables of the differential. Okay, so like we want this whole right side to have nothing but x's or constants. So now in this case, I know my volume is x cubed. I can just punch that in here, and then we get the final solution to be this one. Now what happens is dx dt is describing a dynamic, a rate of change of x with respect to time. So when a lot of time goes by for a cubic crystal that's growing, it will eventually stop growing. And when it will stop growing, what's going to happen is that the change of x is going to stop happening. And that point is called the steady state of this dynamic. And that steady state could be easily found out by finding the values where dx dt goes to 0. And then in this case, you know I must be equals to, oopsie. So in this case, you know I must be equals to x cubed in order to make this whole thing go to 0. And when you try to plug it in, you try to solve for that. When you isolate for this equation here, the x that should make this whole thing equals to 0 is cube root of I. And that will be the value eventually when t goes to 0. Because once the x reaches that point, the dx dt will stop as given by the differential equation. Let's talk about problem 2 now. So in this case, they're talking about a certain chemical. A certain chemical has a production rate that depends upon the concentration of that thing itself. And it's very prominent in terms of chemistry, where you have production of a chemical depending upon the concentration of it inside the whole reaction pool, just like you studied it in chemical kinetics. So now C is the concentration that depends upon time. So C is going to be dynamically changing while the consumption rate is just RC. Okay, that's also given to us. So now the rate of change of the concentration depends upon the production rate minus the consumption rate. So a certain chemical is being produced up in your body at this rate given out here, and then it's being consumed by other parts of the body at that rate. So the change in the concentration of that compound in your body is given by dc dt, which is just production minus the consumption rate. And k, r, v are constants here. In this case, they depend upon your bodily functions and stuff. So production rate is given to us this, and in the A part, they're asking us what is the maximum value of that function. Now this production rate is just nothing but a hill function, and the max of the hill function is just what saturation value is going to be. The saturation value in this case is V, so the max value of PC is just V. In the other part, they're asking you when, at what concentration does your production rate becomes half of its max value. So half of the max value is just V over 2. So when you equate it to the actual production rate equation and solve for C, you can isolate from following all these steps, and then you get C equals to K. That is the point, that's the concentration where your production rate will be half of its max value. Now the second part is saying if there's no production happening, only things that are happening in your body is just consumption of it. So if you turn V equals to 0, the dc/dt is just going to be decaying at that rate with a negative r. And because of the previous WebWorks, we've seen that this represents a very formal decay exponential function. And then to drop by 50%, as the question is asking us, we actually are looking for the half-life of this. And half-life of a certain reaction who follows this differential equation is nothing but ln 2 divided by r. So this is the solution for that one. And now part D is asking when does the concentration not change, which means the production is equals to the consumption. So all you got to do is put dc over dt equals to 0, which means you're going to have production equals to the consumption, and you start solving for this. You figure out the C must be that number. Once you figure out C is that going to be number, and that's the final answer for part D. And now this is where it's tricky. So we're trying to figure out where, at what concentration do you have dc dt as maximum. So if you observe right here, dc dt is nothing but just a function of C. Do you see there? There's nothing but a function of C here. So if you're trying to find out which C maximizes this function, we're just trying to do the optimization here. So the steps for optimization would just be where you take a derivative of this function right here with respect to C using quotient rule. Once you have that derivative calculated, all you got to do is equate it to 0 to find the critical value. When you do so and you isolate for the value of C, following all these steps, you're going to get C must be equals to square root of kV divided by R minus K. And that's it. I just drew the phase line diagram, and we're going to start to talk about more of these things as we talk about in the other problems. The phase line diagram looks something like this, which just literally represents what's going to be happening to this function as you plot it with respect to the concentration C down there. Okay? And that's it. Let's jump to problem 3. Now problem 3 introduces a topic called slope fields. Now for the analysis of differential equations, slope fields are pretty crucial. What it does is, so right now, let's just try to talk about this example. You have an equation describing dp over dt, which means the rate of change of p with respect to time. So p should be a function of time as well, right? So if you're thinking about that, on this axis you have p, on that axis you have t. This should depict a graph of pt, right? Or like a function p, which is having t as its variable, right? So now in this case, when you're trying to see that, there could be multiple graphs going through this which obey this thing. Because of different constant levels, you can scale up the function, you can move them left or right. That doesn't actually make a difference in the analysis. So what slope field does, it layouts a pathway or a set of rules how a function should flow and follow for the next following steps if you start at a given certain point. So in this case, we're given a whole slope field as we see for this in this graph here, and then we're going to have a bunch of points where we're going to start at and then see where the solution will actually go as time progresses. Okay, so let's start at 0, 0. Right now what you have to see is, I don't know if you're probably able to see it or not, but if you're in this very close zone, the slopes at 0 are nothing but horizontal. Okay, so if you start at this point, which is 0, 0, the very first point, as time progresses, you're going to follow the slopes. The slope is always telling you to stay horizontal here, and that's what you're going to do. So that's why if you start at 0, 0, your solution's always going to stay there as a straight line down there. Let's talk about 1, 4. So if you start at something like 1, 4, so you're at this spot. what you got to do is you got to follow the slope field from that spot as time progresses this way. Okay, so if you go a little bit and the slopes are telling you to increase because slopes are just a positive tangent at this level. So they want you to increase, and then they start to become less and less steep and like become steady at a value 10. So what's going to happen to this solution, it will start here, it will grow according to the trend given by the slope field and settle down eventually to the value 10 because that's where the slopes are telling him to settle down. Okay, same thing with 4, 1. So if you start further away on this, but 1 here, you can again follow the trend of slope fields. It tells you to keep on increasing because all the slopes are positive here. As you increase, you're going to saturate to the value 10 here as well. When you start at negative 4.5, 1, that's represented by that point. And then if you do the same procedure, you got to follow the slopes. Slopes are telling you to go increase at this point. So you go increase all the way and then settle down at 10 because it'll eventually merge into that place. Okay, and then for the other points, however, when you start above the point 10, so like in this case, we have negative 10, 12, like on this spot, the slope fields are pointing downwards. So what it says is as the solution progresses, the value is going to go decrease and then settle down to be at 10 because 10 is a steady state, as you would say. How do you figure out steady states from this equation? It's very obvious. Which values do you think makes this equation equals to 0 are called the steady states. So when you think about it, one value is just p equals to 0. The other value will be just p equals to 10. So those being the steady states, you should see completely horizontal slopes here because dp dt must be 0. No matter wherever your solution starts, it should have a slope of 0 when it's at p equals to 10 level or p equals to 0 level. So now the actual question was asking us to tell us the points where the solution will be increasing and the solution will be decreasing. So as we saw, the slopes are always positive in all of these zones. So if you're in between 10 to 0 on a p level, you're always going to have positive slopes, which means your dp dt is going to be positive, which means your solution is going to grow. So all the values of solutions or actual p values, which are from 0 to 10, are going to make a solution to increase and settle down to be a 10. Okay, and then anything above 10, you see all the slopes are just negatively pointing down there. For any value that's going to be above 10, you're going to have a decreasing solution because at that values of p, your dp dt will be negative. You can plug in and check it, or you can follow the slopes as well here. Okay, so now in the C part, they're saying if you start at p at point 0, 0, where would our solution should look like? So we already talked about it. If you start at here, your p is always going to be like a horizontal line, and this line is nothing but p equals to 0. So in this case, we know this is just p equals to 0 for the solution in this case. And then what happens to the values in the part D they're asking if your solution starts at any other point greater than 0? So as we saw, if you start at multiple points like here, or over there, what's going to happen eventually is that you're going to settle down to be at 10 because all the solutions are going to follow the slope field and the slope field becomes stagnant at 10. So whatever is the solution of this equation is going to be, if that initial condition starts at these points or any point above 0, they're all going to saturate to be 10. And that's the idea here. Okay, now we're going to talk about question 4. This is going to do a lot of analysis on the category of steady states, and then we're going to start to talk more about what are steady states and what's happening here. So in this case, we have a differential equation which determines the population of fish given a certain condition here plus a factor of fishing given by HF. Okay, so the first part of the problem, we're assuming there's no fishing happening. When there's no fishing happening, your differential equation will just look like that. So now we got to find the steady states. And by definition, steady states are the value where the differential just goes to 0. So you equate df dt equals to 0 and you solve for it. When you have this equation right here, the two obvious states are going to be f equals to 0 or f equals to 100. Okay, you can solve for yourself and see that. These are the values. So now we got two steady states, f equals to 0, f equals to 100. Now there's something associated with steady states that we call the stability. Okay, Stability of a steady state is how stable is that steady state to disturbances. Okay, so what if you're here, let's talk about that example. So if you're at 10, 10 is a steady state value, right? What if you get a disturbance and you start at a point a little bit above 10? What's going to happen to your solution? Is the solution going to come back to 10 or go away? In this slope field, in this particular example, it's going to come back. So if you have a positive disturbance pointing upward, your solution is going to come back and converge back to 10. And then let's check from the bottom as well. If you start at some point below here, the slope fields are telling you to go increase back up again. Okay, so what happens here is even if you start at the bottom, like all of these points here, you will always come back to 10 no matter what. So now, if you consider the steady state 10, if for positive disturbances that are going up, it comes back down to 10. For negative disturbances going down, it also comes back to 10, which means that 10 is a very stable steady state. Okay, and now we're going to look at the actual examples from where we can actually see how to solve these things using graph and calculus both. Okay, so all I did here was talk about the calculus approach. But what I'll do is I'll skip for this part, and to talk about stability, we'll learn the way you guys learn in the school. So we're going to go by the graphical approach. So what's going to happen is the function that we got for the fisheries, we have the df dt equation. What we're going to do is we're going to construct a polynomial, okay, because what you saw over there in that case is just a polynomial, nothing else. A polynomial in f, okay, a function of x. So to plot the phase portrait, what we're going to do is we're going to make an axis here where the y-axis represents the df dt, and this represents the actual f, okay? So if you were to plot that function that we had over there, where df over dt is nothing but some f times 1 minus f over 100. If you plot that, what you're going to see here is you're going to have two conditions where you have a steady state. It's going to look like an upward facing parabola, a downward opening parabola in other words, okay? So you got to have this thing. It's going to have some value. We're just going to look at the steady kind of diagram here, okay? So now how do you depict the steady states from a phase portrait? There are the points of zero crossing. So wherever the function crosses zero, these points are called the steady states of this function in the phase portrait diagram, okay? So once you have those things come up here, what you can do is now comment on the stability. So now we're going to start at this point here. I'm going to zoom in to kind of help you out, see it. If you are at 0, we're going to test this point for both negative and positive disturbances. So because the x-axis represents the f value here, what we're going to do is we're going to see if you go a little bit before f, some negative point, and you check the value of the derivative at that point is just negative because it's below the x-axis. So having a negative derivative tells you that the f should decrease. Well, f is represented by the x-axis, so if you are here at that point, the derivative tells you to decrease and go backwards. So what you do is you make arrows like this. That tells you if you are at any point before this place, the derivative at that point is negative, which tells you you should go decrease from that point onwards. You're going to keep on going back. Let's check on the right side. So if you're at any point on the right of this steady state, at that point the function's derivative is positive, okay? So having a positive derivative tells you that the f should increase. So if you are at this point, according to the slope, you should increase your value on this side. So you should move towards right because f is essentially just increasing. Okay, so recap here, we're going to talk about the same thing on steady state 100, and we're going to see here. So if you are on some values that are less than 100, the derivative value at those points are just positive because they're above the axis, which means if you are at this point here, you must increase your value as the slope tells you to do so. So what you're going to do is you're going to increase your value, come back to 100. Okay, let's say you're a bit on to the right of 100, and then if you check a value of the derivative at that point, you see the derivative is negative because it's below the axis. So whatever value you are at, it wants you to decrease back to 100. So all you got to do is you're going to put arrows like this. Well, you still show it this way. So see, if you are at 0, you get this disturbance, you go away from 0. If you're at 0, you go a little bit right, you go away from 0. This means that this state is unstable. For the disturbances on 100, however, if you're disturbed to some value that are less than 100, you're going to come back to 100. And if you are disturbed for values of 100 a little bit bigger than that, you're going to come back to 100 again. So this marks a stable steady state. So this is how you plot the phase diagram. You do those arrows and then you represent the stable and unstable like this. On a phase portrait, however, the stable steady states will have these arrows, and then that's represented by a solid dot. Okay, if your state is unstable, then you're gonna say it's an open dot. Okay, so kind of represented this phase line here. This is called the phase line, and combined with this all together makes the phase portrait. So given that situation, we figured out the steady state 0 was unstable and steady state 100 was stable. Okay, so we can comment on the stability from there. We already did here. One key fact that you might have noticed while we're talking about this, you can also use calculus to answer this situation here. Okay, so what you can see is if you make a tangent to the graph at the points of stability, let's say these steady states, if you draw a tangent at 0, the slope is positive. So wherever you have a positive tangent, it's unstable. And at this state where you're stable, you draw a tangent that's a downward sloping tangent, which means if the derivative is negative, then you have a stable steady state. So the previous approach that I talked about, which we skipped through, is called the calculus approach. So all you gotta do is whatever function you have as df dt is gonna be some function of f, right? As we talked about. In this case, the function of f is just that thing. So you're gonna call that g of f, and then for the criteria is if your derivative of that g of f polynomial with respect to f is greater than 0 at a steady state, then the steady state is unstable, which means the slope is positive, that it's unstable. If you have the other case where the derivative is negative, then it's going to be stable as given by this condition. So my g of f function was that. All I did is took a derivative of this function with respect to x. So I did product rule here. You got to take a derivative of 0.2f first, which is just 0.2, and then keeping 1 minus f over 100 as it is. Plus, you got to keep this guy as it is and take a derivative of this, which happens to be just negative 1 over 100. If you simplify that, this is what your derivative is going to look like. So now all you got to do is plug in these f values in the steady states that you found out, this value and that value, and check if you're going to have a derivative that's positive or negative. So I did that. When you plug in f equals to 0, you get 0.2, which is greater than 0, which means this is unstable. And at 100, when you plug it in into the derivative, it's stable. So both the ways are valid. Most of the time in the class, what they want you to focus on is just learn how to find stability using the graphs. But the calculus approach always works as well. We're going to talk about one more example in the future, but let's just go forward. The other thing the question is asking you is the actual carrying capacity. So as biology majors, most of the people know, the carrying capacity is the largest population value that it can safely sustain itself. In mathematics, it means the largest stable steady state. In this case, we had two steady states, 0, 100. The only stable steady state is 100. So that becomes right away our carrying capacity. So now we gotta match the phase portrait in the part here. So as you saw, we should have crossing at 0 and 100, and the arrows should be pointing like this. The only one that matches in this case is D. Okay, everything else has weird steady states, first of all, and some weird arrows as well. Okay, that was easy. Now we're going to talk about the actual part where you start fishing. So now, if you think about it, when a certain ecosystem is stable by itself and you start an element of fishing into it, the largest steady state should decrease to some other value because now you're going to take away some fish from the ecosystem. So the effect is going to be taken away. Okay, so if you do that and you plug in that factor, your differential equation now looks like this. To find its steady states now, same procedure, you're going to put it equals to 0. And once you do so, you put it equals to 0 and isolate for the actual steady states. You get the first steady state to be 0, and the other steady state in this case is going to be 75, which is smaller than 100. that we got in the previous case, and which makes sense because now they're fishing, so it should be stable at a very small value than 100. Okay, so now again, to test the actual stability of these things, what we have to do is start to talk about the graphical analysis. When you do the graphical analysis here, again with the same stuff, if you are at this spot, the derivative is negative, which means you're going to get pushed back. If you're at this spot, the derivative is positive, it's going to get to the right. So you can make those arrows, same thing here. Go back a bit, the derivative wants you to increase the value. Go forward a bit, the derivative is negative, they want to decrease the value. So you're going to come back here. So again, you can classify that 0 is unstable and 75 is stable. And now in this case, the new carrying capacity is going to be 75. Okay, and then when you're trying to talk about the best fit in this case for the phase portrait, what you have to see is, in this case, you're looking for a steady state value of 0 and somewhere 75. So B is going to be the best fit in this case. Okay, and the E part is asking what value of H will lead to extinction. So what you're trying to aim for in this part is whatever steady state you're going to get from the H factor term, you want that to go away. Okay, so if you go back to the expression that you had for df/dt, you saw this term here and you saw all of this term here. We're going to find out where this thing goes to 0. Okay, so we solve for it, we get H equals to 0.2 times 0.2f over 100. Now, because at extinction the f is going to be 0, and when you solve for it, H must be equals to 0.2. And that's exactly what the value of H must be in order to have extinction. Going up.